You guys already set up the live stream.
Luca was helpful.
Okay, you know how to set up
Did
the
you
live
post
stream.
report? We did actually.
I think you did, because I
I'm not sure.
It goes straight to the cloud already?
Yeah, when you do it on the computer, you have to choose cloud.
See how it goes. You have an eraser up there, yeah, on the other side.
All right.
Alright. First in-person seminar, I feel like many things, we might not have chalk or, eraser.
Where's the raise hand button?
Oh, blackboard.
We're encouraging Blackboard talks. That's what I'm going to encourage. That'll feel great.
Is anybody actually on the Zoom?
Yeah. They can speak. Hey, try speaking, Zoom people.
They can't hear you.
Hello.
Okay. Yeah, the volume is not super. Say something, Jonah.
Hi. Can you hear me?
Yeah, it's all right.
If anyone wants to snack their cake pops and some dough as well. Oh, I see.
To the Zoom
This is the
people,
cake
is
that
this
you made.
pleasurable?
This is the third time Anthony brings us cake on a Monday. I think we're pretty lucky.
Good.
Yeah.
Nima made something nicer as well, so.
Oh, did you bring those? Those are so good.
There are also full donuts under that.
What was actually made? We're trying to get a tradition started of bringing pastries on Mondays.
Okay. As long as I only have to eat pastries. No, I'll buy pastries.
Yeah,
No.
awesome.
You might.
Yeah, it was before we get together.
Nice.
Okay, so welcome everyone to our first in-person Kruthoff seminar in quite some time. So we're very lucky to have Jorrit come from Stanford. He's going to tell us a bit about sort of the role of random matrix theory with an external source and sort of how that applies to understanding the role of averaging or not in gravity based.
Yeah, thanks, Edward, and thanks for the invitation to speak here. I guess it's the first talk since 2 years. I feel pretty honored and happy to be here, of course. Never been to Chicago, and it's good to be in a big city. San Francisco is not. Okay, so today I wanted to talk to you guys about a paper that I wrote with Andreas Blommaert last July. It's about gravity without averaging. And okay, I'll explain why these words make sense together. But first, let's just recap a little bit to get everybody on the same page. So I want to start with this picture of, sort of very broadly speaking, what holography is. How I think about holography is a duality between gravity, rather string theory, and quantum field theory. And this gravity theory usually lives in d+1 dimensions, and then this quantum field theory lives in d dimensions. And so pictorially, how that sort of works is the example that we have in West is ADS CFT, where we talk about gravity in ADS. ADS we usually depict as a time slice of ADS as a circle, although here the space, this can be any boundary manifold on the boundary. And the bulk, I draw that here a little bit in purple, is where the gravitational degrees of freedom are dynamical. And what I want to mention about holography in this case is that if I want to do a calculation in the quantum field theory, that means that I'm setting up certain boundary conditions on the boundary, on the conformal boundary of ADS. And I ask, and the dual calculation of that in the bulk is basically asking what ways can I fill that bulk geometry in that is consistent with the boundary conditions. That's an important thing to keep in mind throughout the talk. And then the idea is to sum over all bulk configurations that are consistent with the boundary conditions. We need to sum over everything. So for instance, very simply, if we calculate the thermal partition function on the boundary quantum field theory, that's this particular trace that we're calculating. And in the bulk, that means that, so this theory on the boundary is defined on some manifold, so some spatial manifold like this. And the parameter beta tells us the length of the thermal circle. So if I just draw that picture a little bit different, I have a circle in the manifold, a thermal circle. This has length beta, and that's the boundary condition that I meant here. So I fixed boundary conditions such that the thermal circle has size beta. This manifold here can have some sizes as well, but I'm not going to worry about that. That's all still part of the boundary conditions. So here we have S1 times n minus 1. And now, according to the holographic principle, I need to include all bulk configurations that are consistent with this boundary condition. So one of them is just sort of like a disk type topology. So you can also think about this as just a one-dimensional boundary. That will actually be the situation that we will be most interested in. But then also you need to include any sort of other sort of stuff that you can have in the bulk. So this would be strings, string configurations that are consistent with this boundary condition. There could be branes. This geometry could end on the brane, for instance. And most notably, especially for the talk today, is that there could be other topologies. So other than just disk topology. So here, the circle on the boundary is contractible in the bulk. And well, there could be different ways of filling this particular geometry, especially if you look at this spatial part. Now, the other quantity that you can calculate that will be more or less, will be important during the talk is an object where you take two partition functions. So on the boundary theory, that's just the product of these two traces. But now something funny happens that if we invoke this holographic principle, then what would be the dual calculation? So first of all, there will be the two sort of disk type geometries. This will be length beta 1. This will be length beta 2. But now consistent with that boundary condition is also a connected geometry that looks like this. This is beta 1, beta 2. And then again, there could be these type of configurations as well, connected or disconnected. What I want you to take away from this is that this object is in general non-zero in a gravitational theory. Of course, that's subject to specific analysis, but this connected geometry suggests that there is correlation between the quantum field theory on this side and the quantum field theory on this side. Said differently, from the bulk calculation, it doesn't seem that this is just factorizing. So this puzzle, the fact that on the boundary you just get a factoride, you just get this product, but on the bulk side you seem to get non-factorizing contributions. It's called the Factorization Puzzle. And obviously, and
Sorry, you have a question?
Yeah.
Why don't you have two gravitons? I mean, you have two, different set of copies of the symmetries.
I mean, that will be this configuration will be indeed two of those. But consistent with the boundary condition, if I just give you,
You're imagining it's a boundary condition on the same field. I mean, should I really think of this as taking two separate theories with each where, and have the product of both symmetries?
this would be, that would be in this situation, right? Then you have two of these both theories, they're disconnected, and you just calculate this and multiply it with this guy. But there's another way of filling in the bulk, which is with a single theory, or like, if that is what you mean, then you can have this connected geometry, which is one gravitational path integral. But then with this, the boundary condition is that at these two boundaries. Does that make sense?
It's correct that there are two stress tensors, and the two stress tensors tell you about local fluctuations of the metric near the boundary, and you can fluctuate them independently, so that's not a contradiction.
Thanks.
There's one stress tensor in the second case, right? So it's just one bulk theory.
Oh, the fluctuation is close to the boundary.
The fluctation is close to the boundary.
Two sets of boundary metrics.
Yeah, that's, I think that's what Luca was asking.
Okay. All right, so this sort of suggests that there's correlation, at least if I calculate just this contribution and I don't include any other stuff, then I would seem to conclude that, oh, maybe on the boundary theory, I'm not calculating this product actually, I'm calculating some sort of average. I'm not going to specify what the average is over, but the average sort of induces a coupling between the two sides. So we have this connected geometry. Now, in standard holography, where we say in n=4 super-EMs, there's a boundary theory, it's just a fixed theory. We don't expect that the bulk in the end, when we do include all the contributions, not only this, but also all the branes and everything else, that you should recover again that the boundary theory is just one single theory and it factorizes.
But is there any explicit evidence for that? Like, is there any example in holography where someone has done such a calculation and found that it is actually factorized?
So there is one calculation that I know of course, not in the n=4 super-EMs.
But even in 2D gravity, yeah.
So in 2D gravity, everything seems to be of this averaging type.
Yeah.
And
Even including a full sum of it.
even including, yeah, but it's not exotic enough that there's no, the only way I know where the calculation in this direction has been done is by Lawrence Eberhard in the string theory on ADS3 because it's 3 cross T4 at level 1. Where, okay, he had a conjecture, I think it's proven, but that you would just have this contribution basically.
What does that mean? This is not that topology is not allowed? What does that mean?
Well, I'm not an expert on that particular theory, what the precise conjecture is, but I think is the point is that okay, this wormhole geometry is there. There's going to be other contributions as well, that if you include them, sort of cancel this guy, and you just end up with this. It's vague, I know, it's not like even that is a conjecture.
I thought that string, you were saying that the string basically couldn't, the wormhole wasn't transversable to the string. So you really couldn't connect the two boundaries. I mean, effectively as a picture of what was happening in
Right.
one case. That was very special to the fact that it was string ADS, not bigger.
And I think maybe another reason why you would expect a single boundary theory is, I mean, ADS-CFT is just derived from one string theory. It's basically an open-closed duality. And I guess in that respect, you would just expect there's one bulk theory superstring theory on ADS5 cross S5, and that's dual to the n=4 superangles. I guess that, I mean, there hasn't been some explicit calculation, but that's the expectation. Good. I mean, you're right, there hasn't been an explicit, especially in the n=4 super Yang-Mills community. I don't think they can calculate these type of corrections or things explicitly. And even if you have a lot of control like Lawrence has, there's even there, I think it's there wasn't like a sharp proof of that.
In models where we have like, does this hold for like SYK type of stuff where we could perhaps compute the factors explicitly?
Well, then you would need to do SYK with a fixed coupling. So the SYK Hamiltonian has a random coupling. So if you do that average, then you already be in the situation that, okay, you have the connected geometry and there's no sort of issue. But you would want to look at one fixed set of couplings. That's sort of basically what I want to talk about to get that in these 2D examples. Okay, so I guess so we have two types of, so what I want to advocate is that there's two types of holography. There's one type which is derived from string theory. And okay, you can argue that's the only type of holography we know. So that's ADS5, for instance, ADS5 cross S5, superstring theory on that space, dual to n=4 super Yang-Mills in 4 dimensions. Okay, here many matches have been done, but not in the sense that these guys that I would like to calculate. And then a second one is that's more recent, and it's derived from the Euclidean path integral. Path integral, and that is this recent example of JT gravity. So it's a two-dimensional gravity theory, and a certain matrix model, particularly double-scaled matrix model. It doesn't matter that you don't know what double-scaled means. And this is actually an average over boundary theory. So it's an average over Hamiltonians. And I'll come to what a matrix model precisely is, but it's an integral over matrices. And in particular, in this duality, there's the gravity side. It's a two-dimensional gravity theory. And on the boundary, we have an ensemble of Hamiltonians, and I'll explain a bit more in detail what that means. So this one we've known for a very long time, and it's the more rigorous, the more complete version, I would say, and it's relevant for understanding gravity in its fullest. And this example of holography is simpler, and it's derived. You can basically derive it from the Euclidean path integral. Here it's hard to do calculations, and here it's rather simple to do calculations on the gravity side and on the boundary side. The matrix model side, calculations are also not that complicated. So this second option is nice because it gives you a lot of control. So, yeah.
Derived here just means that you match partition functions and things like that to.
Yeah, this I mean, that, if you take this philosophy, you can derive from the Euclidean path integral that you need all these Weil-Petersen volumes, the volumes of these moduli spaces, and those volumes are controlled by a certain matrix model. So that's some work by Mirsagani and Einart and Orantin, and then you could reverse engineer this side. This duality can also be derived from a two-dimensional string theory. So that would be maybe more in this direction, but just wanted to make a difference here. And in that case, yeah, you can also derive it that way. And then there's the standard duality between minimal string theories and one matrix models. Yeah. All right. Are there more questions? And one other thing I want to mention is that even within the more complicated theories of gravity, you can try to do a truncation or go to low energies, take some supergravity limit. And in that case, when you just look at the supergravity limit, you would find this wormhole geometry as well. And so you would again maybe conclude that even when you just take the supergravity approximation, you have an ensemble of theories on the boundary. So those so two types. So one type that I just elaborated on is what I would call a simple theory of gravity. So it would just contain the supergravity fields. Or maybe even some subset of that. And in this case, you would conclude that the boundary theory is an ensemble. Because of the existence of this wormhole and that you can't get rid of. Versus the other theory of gravity, which would be more difficult. That's those difficult theories of gravity. And this will be the case where you have all the fields beyond the supergravity limit, higher spin fields, fluxes, whatnot. For instance, the type 2B superstring theory on ADS5 cross S5 will be an example of that. And in this case, the boundary theory is a single theory. That's the starting point I'm going to take. So no ensemble. Okay.
Is one meant to be, is one a limit of two? Like
Yeah.
you integrate out
Yeah,
two,
yeah. So there is, yeah, you can go from here by taking some low energy limit. Yeah, that's right. But I just wanted to distinguish these because usually we do calculations within this guy and conclude things about the boundary that might seem confusing at first. But I guess the expectation is that if you do it in the second case, in the full thing, you'll get the answer that you think is correct, a consistent answer, and there's no factorization puzzle.
Do you have some sense of how the ensemble averaging emerges out of taking the limit, the low energy limit?
I think that's a very interesting question. I don't know how this, I mean, it could be that you're integrating out some fields, and maybe you can see that as well as doing some averaging. Like the average could also be an energy average, where you just don't care about the UV physics that much, and that energy average would result in a calculation in the supergravity limit. Like if you compute some observable and you plot it as a function of energy, it might look very complicated, but maybe if you do some moving average or something like that.
Whatever it is, you should see it come out of the low energy limit.
Right.
Shouldn't it be particular to gravity though? We usually don't make this claim when we talk about standard RG of quantum field theories.
Yeah, that's,
Yeah,
we
we
usually
don't keep track of the spectrum.
We're not keeping track of the spectrum in one. Right, we throw
Right,
away all
you
the
lose
operators.
the spectrum in one. I mean, you kind of only have some average properties.
No, but I mean, the low energy RG limit of a QFT is usually still approximated as a QFT, a unitary QFT. Not as an ensemble average of such things.
Yeah, but here you have a situation where
Godspeed.
here you have a situation where the IR limit has a continuous spectrum, right? Because in the presence of black holes, classical gravity says the spectrum is continuous.
yeah.
So there's some UV-IR mixing going on that we expect that degrees of freedom that we're integrating out are nonetheless, creating some kind of average that makes you think that the black hole spectrum classically is continuous. And that continuous spectrum should be interpreted as saying you have some energy resolution in the low energy theory, and every black hole state that lies within that energy band is just counted in the semi-classical contribution. And that's the sort of averaging that I think Jorrit has in mind.
Yeah, I think that's right. Yeah, thanks for that, Emil. Yeah, it's indeed true that the spectrum will be continuous.
That's not the case in supergravity limit of radius 5 cosine 5, right? There's
Well,
no
the
continuous.
state, as Emil was saying, the black hole spectrum will be continuous.
Yeah.
Okay. All right, so let me just explain a little bit more about the first, the JT gravity, which would be an example of that sort of simple theory of gravity.
How about it works, by the way? In case it's
Even like. Huh? Thank you.
Somebody draw that line before.
Yeah, I drew it before, I just completely forgot. All right, so simple theories of gravity. Great. So the simple theory of gravity that I have in mind is JT gravity. And its action here is very simple for those who don't know this. So this indeed qualifies in my sort of very vague definition as a simple theory of gravity. It has a scalar field phi, which we call a dilaton, and then there's the metric degrees of freedom here in the metric. This is the Ricci scalar, and there will be a boundary term whenever this manifold that we're considering has a boundary. This theory is just about hyperbolic spaces because two-dimensional hyperbolic spaces, because phi here acts as a Lagrange multiplier. That makes this theory also simple from a calculational point of view. And this gravity theory is dual to this dual double-scaled matrix model. And that looks like this. So the matrix model. It's So one matrix model, there's some potential, some probability from which I draw, some probability distribution from which I draw this H's. And then here I can insert operators that depend on this Hamiltonian. And what I end up calculating then is averages of this operator that I inserted. Examples of O are trace e to the minus beta h, so partition functions, or I can calculate products of partition functions. Like this. Now, and in the matrix model, we can calculate this. There's a topological expansion in the matrix model that matches onto the topological expansion in JT gravity. And so from the matrix model, there's a lot of control, and you can match that also with the gravity calculation. And the sort of the new thing about this JT gravity is that you can think of this H as really as the Hamiltonian on the boundary. So there's a precise sense, and this you can see clearly if you consider JT gravity as a limit of these minimal string theories, that duality between minimal string theories and the one matrix models been studied a long time, since the beginning of the 90s, end of 80s, and there's a certain limit of those theories that reproduces JT gravity. And in that limit, what happens is that the world sheet gets asymptotic boundaries, and so you think of the world sheet as the spacetime, becomes the spacetime of JT gravity. And so what I want to do today is, first of all, I would like to find a theory that is sort of medium difficult, that is in between these two. And why is that? Why do I want that? First of all, like the top one, the simple theories of gravity, we have more control. We can calculate things. Whereas the second one is more the goal. This is what we want to understand. So if we can have something in between, that would be great, at least in my opinion. Medium difficult. And so what I will be talking about is the procedure of how to do that. And then we'll talk about some lessons.
Excuse me, short question. Usually these matrix models could be used to describe two-dimensional gravity, right?
Yeah.
Whole story, especially in the scaling in the limit.
Yeah.
Is this something specific to JT gravity? Does this correspondence, is the correspondence the same?
Yeah, it's the same. So,
But why you focus on JT gravity rather than just regular two-dimensional gravity?
so the minimal strings, I guess you know more about this, so let me just tell you. So the minimal strings that JT gravity arises from is from the 2, p series, where you send p to infinity. And the reason why this is an interesting example is because if I don't take this p to infinity limit, then this matrix model, I cannot think of this as the boundary Hamiltonian, or there's some quantum mechanics living on the boundary. And that interpretation only comes available once you take the p to infinity limit. Because the p to infinity limit is accompanied with a low energy limit of the minimal string. And that sort of forces these boundaries to be very large. And that's why this is a useful, then it becomes really an example of holography. Yeah.
So if you took this matrix model and took the probability of distribution for the eigenvalues that it generates, and then you said, let me just choose randomly a set of eigenvalues from that ensemble, that presumably would be the analog of n equals 4 Yang-Mills, right? It's a theory where the eigenvalues are not fluctuating. They just just magically have the right probability distribution to correspond to JT gravity. So would that be an example of a factorized theory?
Yeah. I mean, that's precisely what I will talk about.
Oh, okay.
Yeah.
I'll shut up then.
That's right. Sorry?
25.
Yeah, good. All right, so what I want to do to construct this medium difficult theory of gravity is indeed, as Emil was asking already about, is to try to make a boundary theory that is a single theory. What would that mean in this picture is that I just take one H from this ensemble with this probability distribution. And so there's a very simple way of doing that. It's namely changing the probability distribution. This JT, and now I insert a Gaussian. H minus H naught. So this will be now my probability distribution. I can insert some operators. And now, as a function of this sigma, the width of the Gaussian, I can tune to be either completely random, like the JT example, where sigma is infinity, or I can take sigma to be very small, and this Gaussian is sharply peaked when H is equal to H naught. And in that case, you would have a single draw from the ensemble. And of course, here I'm assuming that H naught is picked from this initial ensemble. So this will basically be the matrix model that I want to study. And the question now becomes, what does this guy mean in gravity? What does this mean in gravity? One of the things that is often useful in studying matrix models is to diagonalize H. So you write H as U, lambda, U dagger. And often what happens is that the unitary integral decouples, you can do it, and you are left with a distribution of an integral that just depends on the eigenvalues. If you have that, you can also introduce a density of eigenvalues, rho of lambda. In the large L limit, this will be this continuous density that Emil was mentioning before. And in that case, calculation of traces becomes very simple because those become integrals. And we can work with integrals more easily than traces, I guess. We can do saddle point approximations, calculate the large N, large L limit of this density. And that's all great, and we can calculate a lot of things. But now the problem is that this Gaussian sort of contains a term that's trace H times H naught. And this term will still depend non-trivially on the unitary integral or on the unitary U. And so you can't pull out the unitary integral, do the unitary integral, and have a distribution that's just given by the eigenvalues. Okay. Now, so the unitary integral that you're left with has this form. for these lambda and h naught, I can both make them diagonal. This integral, luckily you can do exactly. It's called the Harishandra or the Harishandra formula. Harishandra was like 20 years earlier than Harishandra. So I'm just going to write that. And this is approximate. I mean, this is exactly up to some prefactors given by this formula. Lambda I and xj. So this is the determinant of this matrix with these entries. Lambda are the eigenvalues of the matrix H, and x are the eigenvalues of H naught. And then there's some other factors here, some van der Monde factors. And well, the way you prove this is using this integral turns out to be one loop exact. So you can calculate the saddle points and the one loop determinant, and you'll get that answer. In gravity, however, we would like to do a double scaling limit. So that means that we zoom in close to the spectral edge of this density of eigenvalues. So have in mind here for this density of eigenvalues, say in a Gaussian matrix model, I'm sure people have seen the Wigner semicircle. And gravity is sort of defined, the gravitational description emerges when you zoom into one edge. Send L to infinity, size of the matrix to infinity, and zoom into this edge. To do that, for this particular piece, so stick this into that matrix integral and double scale this. This is going to be very complicated. We didn't know what to do with it. So there's a bunch of avenues that you can take here. So one of them is take the potential. So here I wrote JT subscript all the time, but you can take any potential. You can take it to be a Gaussian matrix model. In that case, you can do everything exactly. So this is analytically tractable. And so I won't be talking about this, but in the paper we discussed this example to gain some intuition. One thing that happens is that as a function of sigma, so let me draw sigma like this, and let's consider the spectral density. So rho of lambda. You start off with the semicircle when sigma is close to infinity. So you just have some nice eigenvalue distribution. But then when you make sigma smaller, this is not what I wanted to draw. When you make sigma smaller, what you see is that there's sort of large ripples emerging on the eigenvalue distribution. And if you make it even smaller, it actually transitions into a lot of small eigenvalue islands that are all situated around the eigenvalues xi of your matrix H naught. And eventually, when sigma is really zero, this just becomes a bunch of delta functions. So precisely as you would expect.
The average density is still the same, right? If I kind of smooth your delta functions, I'll
Yeah,
get the same shape.
Mm-hmm. Yeah, that's sort of the statement that if I do the integral for H naught there, this Gaussian goes away. Okay, so then, but this is not very gravitational yet. Maybe some people at Stanford think finite L matrix model is still gravitational. Maybe I don't. So the second point, second approach that you can take is sigma to infinity and work perturbatively around that limit. So that's perturbation theory around JT. And here you can expect a more gravitational discrete interpretation. Then lastly, so there is also, I guess the more interesting limit is when sigma goes to 0. Part of the problem with this limit is that you end up in a situation where the eigenvalue density is multi-cut. So there's means that there's different islands that are disconnected from each other. The gravitational description, as I was saying, arises when you zoom into an edge. And while that still is possible sort of for this case, in this situation, it's not even clear why you take the double scaling limit. Like, okay, what edge do you pick? And so there, it's not clear what to do with that. What you can do in this situation that we won't be talking about, that I just want to mention, is that instead of keeping all of H naught fixed, you can average over part of H naught. So for instance, you can keep a few eigenvalues fixed and average over the rest. So then you would end up with a 2-matrix model. So you integrate over H naught and localize some of the eigenvalues. So this is more this eigenbrain picture that Andreas and Thomas Mertens developed. And that is a way of studying this particular sigma to 0 limit.
But I didn't understand what you're saying, that if you don't know which part of the spectrum to focus on, because I mean, even when it's delta functions, we know that, like, if I, without even averaging on H naught, I know that if I kind of smooth your delta functions, it's going to look like the left plot again.
Yeah, that's what I was.
Yeah,
That's what I meant with.
right. I mean, if your H naught is chosen. So then you know what part of the spectrum is supposed to reproduce gravitational stuff, even if it's delta functions.
Yeah, but these delta,
Which is what, the edge of the first one?
Which becomes the edge of the first one upon smearing.
yeah, it might be that maybe you just pick the edge of the first one, but
No, well, it's going to be a bunch of them, right? It is.
Yeah,
When
but
the
what-
sigma goes to 0 limit, it's a bunch of delta functions.
but then you would have a like a tensor product of gravity theories. Yeah, is that the interpretation? Maybe that could be.
Sorry, I also missed this point.
Yeah.
Edges in this simple the matrix model, edges are usually described by in the limit by airy functions.
Yeah,
All kinds of distributions, they are well known on the edge. What is the problem?
You mean that when I zoom into this edge, you get the airy functions and so, yeah, that's right. That's true.
But then what is the problem? I missed the problem.
So the problem is that when you do a double scaling limit, you would zoom into this edge, right? And it doesn't matter whether you do this or that edge. But when you have these multi-cut solutions, which edge you take, I don't know which edge you should take.
Multi-cups means what? Support is many on many intervals, right?
Yeah, support is many intervals.
And then what's the problem?
So the problem is then that, okay, I have all these different eigenvalue distributions here. And each of them, each edge that I zoom into, whatever edge I take, there will be a gravitational interpretation. But to me, it's not clear what the prescription there is. Like, should I take one specific one, or should I sort of sum over them, or is there some? Because each edge will give you a gravity theory, yeah, so then it seems that you get a tensor product of gravity theories or something like this.
Are you thinking that those distributions on the edge characterized by P, right?
Yeah, that's right.
So you think that they could be all different, or it's the same P? Then if it's the same, then take any. They're all identical, if different, not.
Yeah, but I want to have this information about this H naught. That should still be present, or that's something that I want to preserve in the limit. And yeah, when I just take all of them, I might lose that information. I don't know how this information about where this peak is localizing that enters the calculation when I do the double scaling towards any of these edges.
Sorry, what's the what is the scale on the right-hand figure and then the middle figure?
So
What's the spacing between the peaks? What's the height of rho?
So the height here will get to become infinitely high, right? These will just be Gauss. These will very tight semicircles, but very large. And if H naught is chosen from the JT ensemble, the spacing would be e to the minus S naught.
Okay.
Or it will be very small. Yeah.
Okay. So
so this is an extreme situation. This is an extreme situation.
Isn't the dual supposed to be stringy for a fixed H naught?
I think, I mean, I didn't put any of those ingredients in, but it could be that this guy on the gravity side means that I need to take JT gravity, put some other stuff in it. And indeed, in this limit, you'll find that. So I can explain that now.
Okay.
yeah, but,
Emil, did
yeah, so it just seems to me that if you're trying to sort of freeze the individual eigenvalues as being sort of the centroid of each Gaussian,
yeah,
then you know what you originally interpreted as the gravitational computation of correlators is the sum over all of the eigenvalues, you know, of your favorite moment or whatever you're computing.
right.
So it's not that the gravity answer comes from focusing on one particular edge or collection of edges. It comes from the sum over everything.
Yeah, good point. Yeah, I think I agree with the statement that, oh, you just need to include everything. But yeah, it's not, I don't know the precise prescription. Yeah, what the idea there would be. But something like that would indeed be my guess as well. Yeah.
Excuse me, one more comment. Normally, you may consider potential which produce multi-interval support,
Yeah.
disconnected support. Normally, it's interpreted as Riemann surface of higher genus, and genus is computed out of number of intervals, right? In JT gravity, which you wrote, constraint seems to be fixed curvature, scalar curvature to be -2,
Yeah.
which means topology of a sphere, right?
No, that's R is 2. So -2 is any genus Riemann surface. So any genus G, like
Greater than 1.
greater than 1. Yeah.
Okay.
Yeah.
So then what is? Yes. I'm sorry. So we fix the curvature to be curvature is constant negative curvature. Genus could be arbitrary.
Yeah.
But zero. But zero and okay. But except sphere and torus. But then it will be. Then what's wrong with that interpretation? Maybe this number of supports corresponds to genus.
I don't know about the why a multi-cut would correspond to many genus. Maybe you mean that when you have two.
Writing rho as an analytic function.
Yeah, exactly. That, if you have two cut, that would be like a torus. Yeah, that's true, but that's not sort of what corresponds to the geometric topological expansion. That would be the if you analytically continue this guy, as Clay was saying, you will get different types of topologies, but that's not the same as the topology gravitationally. In the gravity,
It's different.
yeah, it's different. Yeah,
Not related.
yeah. There's no problem with there's no problem with this. It's just that I find it curious that you have these multi-cut guys, and what's the prescription? Usually, when I think about double scaling is you scale towards one edge. Now there seem to be many. What do you do? It seems that, okay, you need to include all of them, or yeah, and what's the precise prescription there? That's the question. There's nothing wrong with this. Okay. So since my time is almost up, let me just
For about 10 minutes.
yeah. So in this large sigma limit, what are the lessons? Yeah. So I already told you about these multi-cut things. So there's, besides that, at large sigma, what we get is that JT gets modified to JT plus a non-trivial dilaton potential. So usually the dilaton potential for JT is just linear. So that's the 2 phi there. But now when I try to fix some of the eigenvalues and I'm in this limit, this potential gets modified. This is more like a closed string picture. There's also a more open string picture where this potential can be interpreted as JT plus FCCT branes. Or to be very precise, ghost FCCT. Ghost is like anti-brane in for normal D brane. And second lesson at large sigma.
For those of us who are unfamiliar with the terminology, ghost does not mean anything anti-unitary or non-unitary?
No. It so an FCCT brane in the matrix model means a determinant.
Yes.
And a ghost brane is just an inverse determinant. So it's like, yeah, you like in an empty brane, you flip the sign of the tension, or it's like a negative tension brane.
A negative tension object would is like having a negative energy, right?
I guess so, yeah. It's just the difference between writing e to the trace log or e to the minus.
I'm trying to determine if it has some physical sickness or not.
Yeah, it will. Yeah. That was actually my second point. So lowering results in a phase transition. And this phase transition is, so I won't have time to discuss that, but I can. Okay, so lowering sigma results in a phase transition where the spacetime can end on these branes. But when you make sigma smaller, what happens is that the boundary on the branes becomes very large. And this was actually a transition that was already studied by Kazakov, I think in 91 already, where there weren't even brains. And so, yeah, but it's really brains that he considered. So let me just maybe quickly mention why we get these branes appearing.
Sorry, with the phase transition to having you mean to having another asymptotic boundary?
Yeah, they become very large.
But
I
that,
don't-
I mean, we're trying to, don't we get to fix the boundary data?
Yeah, good point. So I don't want to think of it as an asymptotic boundary, but just very large. I think
It's large but not infinite or something? What, I mean, doesn't scale or something? What does it mean?
it's a boundary that has extrinsic curvature. And if you translate it to gravity language, what that boundary is, it has extrinsic curvature 0. Whereas the asymptotic boundary has extrinsic curvature bigger than 1. That's the difference. But the length would become very large. Yeah. So let me quickly mention how these FCCTs appear. So the unitary integral was this guy that we needed to calculate. So this angular brackets is an average. So I'm going to be quick here, but this guy, of course, I can write standard identity as in this way, and I only take the connected correlators. Now, this connected correlator you can calculate using Weingarten's. That's just a fancy way of doing the unitary integrals. If you take the leading correction, or the leading term in that calculation, leading and in L, what you find is this. And this, of course, is a product of L inverse determinants. And I took out some factor. To write this. This is not an exact quality.
Angle brackets was integral over U.
Yeah. Yeah, so this sum over n gives you this log, and then this sum over L is the sum over these eigenvalues xi, and that turns into a product of these determinants. So I have many determinants. Well, in the double scaling limit, L goes to infinity, so I have an infinite number of branes, and so that's why you will end up with JT gravity plus these branes. And you can already see that. So when when sigma, did I write this? So when sigma becomes smaller, you can eventually hit some of the eigenvalues of H, or you will enter into the distribution where the eigenvalues of H have support. And in that case, this determinant would vanish and this guy would be large. And that's precisely when this transition happens. So that is roughly speaking what happens there. Now, in the remaining minute,
What is the critical sigma in terms of other?
Yeah, that's related to the largest negative eigenvalue
Of H naught.
of H naught, so this xi, and the
H
value of the spectral cut of the
U lambda.
eigenvalues of H. So H has some support, and when
So this transition probably doesn't depend, or for that transition, it doesn't matter that H naught is random. It could have been a very poorly chosen H naught.
I mean, it's to analyze that transition, to see that there is a transition, I mean, you need you analyze it using all these techniques that.
Right, but it's kind of you're doing a large sigma effect, so probably H naught actual, like in the sigma goes to zero limit, H naught has to be, better be
Yeah.
chaotic. But
Yeah,
here it probably doesn't matter. too
Oh,
much.
yeah, oh, that's right, yeah, that's right, yeah, that doesn't matter, that doesn't quite matter here, yeah. Like this would happen with any of these inverse determinants. This could be some number, and then this transition would also happen, yeah.
I don't know if all the x's are the same.
So final thing. So with this change in your matrix model, you can also calculate the eigenvalue distribution. And you can even take the double scaling limit. Like these branes, we know how to think of them as in the double scaling limit in the geometric picture. And that's where really their interpretation as branes comes from. So these are places where the geometry can end on. And yeah, that's what they are. So this guy you can also interpret in a more closed string picture. So you can calculate the density of states, the eigenvalues. And what you find is just the JT answer plus here there is a small shift. And then there is a precise correction that you can calculate coming from the infinite number of branes. And then here there's some coefficients. So these coefficients depend on all the eigenvalues. Okay, so the density of states gets modified in this way. There's an infinite number of terms here, and that comes from the fact that the trace log, when you expand it in powers of h, contains any power. And the dependence on the eigenvalues is in these coefficients alpha k. And you can see here that when this guy becomes zero, something funny is going to happen.
What is E naught?
So E naught is the value of the spectral edge. That can be non-trivial here. So I draw the density of state, rho of E. This will be E naught or minus E naught in my conventions.
Okay, thanks.
And the E naught in this case with these branes is order is suppressed in the topological expansion. So for those that know a bit more about JT gravity, this goes like e to the minus S naught. So it's suppressed in topology, in the topological expansion parameter. Now, this density of states you can also convert into a eigenvalue in the dilaton potential, to change in the dilaton potential of JT. And that will be the final thing I'll write down. I'll e to the
This we can trust at large sigma. Is that the statement?
Sorry?
This we can trust at large sigma
Yeah,
before the transition or
absolutely. So this density of eigenvalues, you can translate into a change in the dilaton potential, JT. And the correction takes this form. And so I think I dropped the E naught here because there's E to the minus S naught already here. So to leading order, I can drop that in this expression. And here again, you see that the dilaton potential has a dangerous divergence that can occur. And that's again related to this phase transition that happens when I lower sigma. And it's again related to this divergence as well. Let's see. So a few things. So what did we learn from this? We saw here that the bulk theory, so instead of this sort of simple JT gravity, where we have all the averaging properties and all that, here we see that if we go away from that ensemble averaging, the theory becomes a bit more complicated. We get these branes that enter the game, and we need to take those into account as the effect of changing the dilaton potential a little bit, and eventually, when sigma becomes small enough, even results in a phase transition. Okay, I didn't have time to talk about that in detail, but I'm here till Thursday, so you can bother me about that, definitely. Yeah, so that's all I wanted to say now. Thank you. Sorry for going a bit over time.
Started late. Do the brains have like both degrees of freedom?
These branes, no.
Even though they have some negative energy that suggests that something can get excited on them.
I mean, you can always, there's one way of thinking about these determinants as in the following way. So, I look at this determinant. I can always exponent. I don't need to do this. I can consider this as this particular integral. So, and this is, yeah, people in this ribbon graph business and sort of the older latent matrix model literature thought of these determinants in this way, where these size are like the quarks in the matrix mod in QCD. So in that sense, you can maybe think about these degrees of freedom as living on the brain, but they're not dynamical. They're just Grassmann numbers.
So I got a little lost in what was happening here with this phase transition. So this sigma, the point of the point of the phase transition is when sigma approaches the inner eigenvalue spacing, or is it something else?
No, it's when an eigenvalue enters the cut.
But I'm confused. The H naught and the H are drawn from the same distribution, so they should both be in the cut, right?
You're absolutely right. So the double scaling limit that I had to do to sort of make sense of this object required me to scale sigma and these xi's also in a way that sort of forced them all to be outside the cut. It's a bit artificial. It's maybe not what you would have in mind, but that's one way where we could do analytic calculations and see what that meant. Yeah.
Okay, so you're working then with matrices H naught that are not drawn from the ensemble.
In the end, no. Yeah, I think
Okay.
that's right. Yeah. Yeah. And it's again related to this entire issue of this breaking up of the density of eigenvalues and this doing this exactly and trying to interpret that geometrically was very complicated, or yeah, we didn't manage. So what we did is look at what happens when these eigenvalues sort of start entering in the cut as an intermediate stage to.
Yeah, it's a little confusing because, I mean, the matrix integral you started off with didn't seem to have any sort of pathology when the eigenvalues of H naught and H were intermingled.
You're absolutely right. And I think that this transition might be an artifact. Because even non-perturbatively, like the eigenvalue distribution has support everywhere. So I think if you calculate this non-perturbatively, like say you calculate the insertion of one of such inverse determinants together with your partition function, for instance, that non-perturbatively it might not have this transition, so it gets resolved. You understand what I'm saying?
Yeah, yeah. Okay, thank you.
Yeah, the same as like determinants. They're like entire functions, right? You have the Airy function and okay, the inverse determinant, if I calculate it, it's a combination of Airy and Berry. And those are all smooth entire functions. So yeah, but yeah, that's one suspicion, but maybe it's not true. Maybe there's another effect that comes from higher order corrections that I dropped in this process. That might be important. But in the end, I do believe that this transition is an artifact. Yeah, I'm not. I don't think it will happen all the way.
Okay.
Yeah. Thanks. Yeah.
I'm not an expert, so can you just relate this back to the big picture for me? Have we learned something about the factorization puzzle?
Well, I think what we've learned here, of course, with the caveats that okay, this is still at large sigma, so I'm still at close to the JT limit. I think what we have learned here is perhaps how JT gravity gets modified and how sort of branes, which I think will be important also in the higher dimensional case, play an important role in trying to resolve this this factorization puzzle. But I mean, it's still at large sigma, so yeah, there's still, I think, more work to do.
Thank you.
Thanks.
The fixed spectrum is basically at sigma equals 0.
Yeah, the fixed spectrum is at sigma 0. So in the Gaussian case, so then you can even like write down exact expressions for rho, and then it's still pretty complicated because all the eigenvalues need to enter it in some way, and basically you get like an ugly sum over all the eigenvalues that you then interpret as some contour integral. So there's some manipulations there to make it prettier, but still it's a complicated expression, but it has the correct behavior. So at large sigma, you get the semicircle back, and at small sigma, you get the sum of delta functions. Yeah.
So in that case, did you have the issue of having to pick H naught not from your distribution?
No, there was no issue like that. No, so that's another piece of evidence why maybe that transition is not.
That was a finite end that you were doing those, right?
Yeah, precisely. So that might be that.
Transition anyway.
Yeah, yeah, that's right. That's right. Yeah.
Maybe what's going on is that when the eigenvalues are very well separated between H naught and H, then I think there's some kind of effective potential that develops for the angular degrees of freedom. That they'll have some sort of a saddle. But when the eigenvalues start to coincide between H naught and H, then
Yeah, I see what you mean, yeah.
then the UN there's some kind of UN symmetry that,
Enhancement, yeah. Mhm.
you know, that the UN sort of drops out, or I'm not quite, I have to think about it more, but maybe by thinking about what's going on with the angular degrees of freedom that you're trying to integrate out, you might get some intuition about what's happening when the eigenvalues start to intermingle.
Yeah, that's a good point, yeah, yeah, thanks, but, yeah. Mhm.
The rest of the questions for those who want to stick around, and if not, I think we can probably thank the speaker. Yeah.